So let's finally get to some applications for these transmission lines. We'll look at essentially three specific applications which are quite intriguing, right? I would say. So the first application is a quarter wave transformer. Okay, so this is a very fascinating phenomena. In fact, we will see this, right? You may be curious to understand that the same logic that we are going to show for a quarter wave transformer can also be used to explain the color of bubbles, right? Soap bubbles. Let me have you scratching your head till the later in the course, where we'll see how quarter wave transformers in circuit lines can help explain the colors of soap bubbles, right? So, but till then, we will just look at the circuit implications here. So, we are looking at lossless lines, and more often than not we have a situation, so lossless lines and say for real loads. Okay. Although the second constraint of this being applicable only to real loads is a rather weak one, but nevertheless, right, this is a very typical concept that is used to try and remove or mitigate reflections, right. So oftentimes it is impossible to get to ensure that your load is always going to be the same as the characteristic impedance of the line, right. So my RL, load resistance, is not Z0, right. But still I would like to ask the question, can I get rid of reflections from such a load? And perhaps I can do so at least at a very specific frequency, right. Let us see that. So I have a generator, I have a transmission line of Z0 and D, and this is connected to an RL. Okay, and RL is not equal to Z0. Right. So we are going to use the fact that if you can recall, when we were talking about periodicity on lossless lines, what did we say that the impedance transforms itself to when we move quarter wavelength, right, away from the load? We said that the impedance inverts itself, right. We said that for lambda by 2 the impedance is exactly the same, right. So that is the periodicity, but halfway through at lambda by 4 we said the impedance inverts itself, right, which is to say that Z at L plus lambda by 4 is Z0 squared by Z at L, right. So this was the relation we saw during the discussion of periodicity. So we are going to look at this, right, closely, and we are going to ask ourselves, if I have a situation where RL is not equal to Z0, what can I do, right? So let us look at a situation where I can insert a transmission line of a very specific impedance. right, and the length of this is lambda by 4, okay, and it has a characteristic impedance that is Z0 prime. So I design a new transmission line that is not Z0, right, and I would like to transform this load impedance RL, right, to Z0, right. So I want this transformed impedance to match my original transmission line, right. So what would this, so remember that I am transforming the impedance RL through a transmission line with a characteristic impedance that is different from the original transmission line that I had of distance d, right. So I am inserting a new transmission line with a different characteristic impedance with a very specific length of lambda by 4, right, and I am seeing how this impedance can be transformed using this transmission line such that the transformed impedance at the end of lambda by 4 transmission line that I have newly created matches the value Z0, right. So Z at the load is RL, okay. So I actually seem to get a solution where the transmission line impedance Z0 prime is the geometric mean of the characteristic impedance of the original transmission line and the resistance you have, right. So for example, if say Z0 is 50 ohms, this is very typical, and then your RL was 100 ohms, okay. If I were to insert a quarter wave length, right, electrical length of 1/4 wavelength of an impedance which is the geometric mean of these two, this is essentially 100 by root 2 roughly, okay. So if I insert a transmission line with a characteristic impedance of 70.7 ohms and a length that is quarter wavelength, then what I see is the resistance RL, which is 100 ohms, transforms itself to 50 ohms by the time I hit the junction of Z0 and Z0 prime, right. And now this 50 ohms perfectly matches, so there is no reflections anymore, right. So the original one, I had RL that is connected to Z0, right, and the reflection coefficient there would have been, right. So if I had not put this quarter wave transformer, so I am going to say without transformer, I am going to say QWT for short, okay. QWT stands for quarter wave transformer. So the reflection coefficient without the quarter wave transformer would have been 100 minus 50 by 100 plus 50, right. So this is 1/3, right, and a voltage standing wave ratio would have been 2, right. So the maximum to minimum voltage would be a factor of 2, right. But now miraculously at this very specific frequency corresponding to lambda, right. So remember that this length is very frequency specific. How do you get lambda? I will probably give you L and C for the transmission line, right. For the Z0 prime transmission line that you are creating, you will probably have the transmission line parameters. From here you can get beta, which is omega square root of LC, and lambda is 2 pi by beta, right. So for a very specific frequency omega, right, because I cannot have a variable length, right. So I'll have to design this transmission line of a very specific length. Once I design it, it corresponds to for that frequency, right. In fact, you can say that's the drawback of the quarter wave transformer, it is very, very frequency specific, right? But if you can say that the operating frequency ranges is very, very narrow and it is around a very specific frequency, I can create these quarter wave transformers that can essentially map the resistances into different loads that then can be made to match the value of the characteristic impedance of your original transmission line, right? So I would say that this is a very, very nifty idea to remove reflections, but nevertheless it seems like it requires the need for a new transmission line to be designed, right? So there's a Z0 prime transmission line that I need to design and the interface of this transmission line to the new line, okay? Nevertheless, I do encourage you to think about what might be happening to the V plus and V minus voltage waves. How is it that deliberately by adding another source of reflection, right? So remember that in the original case, I only had one point of reflection, right, which is between RL and Z0. In the quarter wave transformer, I now have two locations where there is a discontinuity in the impedance, right? So very rarely do you find solutions in nature where adding more trouble gets rid of the original issue, right? So I have actually added one more deliberate reflection and somehow these two reflections together miraculously cancel all reflections going back to the source, right? So I'll let this be a sort of a creative exercise for you to sort of ruminate on all the new topics that you have learned and the concepts that you have learned in trying to explain how this quarter wave transformer is able to mitigate reflections, right? But nevertheless, the mathematics seems to be simple, that I simply need a transmission line of a very specific length, lambda by 4, with a characteristic impedance as the geometric mean of the load and the characteristic impedance that I would like to match it to, right? So I said that the requirement of this quarter wave transformation technique is restricted to real loads, but that's perhaps not quite true, because I could always transform any complex load to a purely real load, right? Because if you remember, when we talked about the voltage standing wave ratio rho, that the points of maximum and minimum voltage swings, right, occur at positions where the impedance is purely real, right? So I can always transform a complex impedance to a real impedance by just adding an appropriate length of a transmission line, and then the problem becomes matching this real load to the characteristic impedance Z0 through a quarter wave transformer, right? So you can sort of combine these two logics and sort of extend it to a comprehensive set of loads, complex loads, right? All right, so the second application we look at is using transmission line elements as circuit elements. Okay. So for this discussion, I'd like you to jog your memory to the mystery problem that I had given to you early in this unit, where we looked at a simple capacitor and resistance circuit, and we noticed that the behavior of the capacitor changed from being a capacitor, an ideal capacitor, to an ideal inductor by just changing the frequency, right? So at high frequencies, we noticed that a capacitor doesn't seem to act like a capacitor but more like an inductor, right? So which means that our traditional notions of building ideal circuit elements like capacitors and inductors have their own drawbacks, right? And this, I think, in that specific example in the mystery problem, I said was attributed to the leads, the long leads of the capacitor. But nevertheless, there are these challenges, right, when it comes to building capacitors as we know them in the toy models. Tends to have these additional concerns, right, which is the leads attaching the parallel plates to the circuit in itself is now relevant, right, at high frequency operations. So instead of having to build capacitors with parallel plates, right, in the traditional sense of copying the toy models, you can actually now use transmission lines and segments of these transmission lines that mimic the behavior of ideal capacitors and inductors at high frequencies, right. So for this, just let's recall that the impedance transformation equation right. So we look at two specific cases where ZL is 0, in which case Z of L transforms to J Z naught tan beta L. I'll let you take a moment to just derive this, it's very quick. And other scenario where ZL is infinite, which corresponds to open circuit, right. So short circuit and open circuits are very easy to make. So I just connect the two leads of the transmission line to get a short circuit, or just leave them floating or open to get an infinite impedance. But what is surprising is that even though the load impedance is 0 or infinite, once I have a transmission line of certain length L, I transform these short circuit and open circuit impedances to purely reactive impedances. Okay, so as I change the value of L, right, going from the load towards the generator, I notice that the impedance transforms itself into purely imaginary values, right, or purely reactive elements. And the fact that tan and cotangent go through all real values, right. So for example, tan beta L is a function, so 0, and it goes all the way to infinity at pi by 2, right. So this is tan beta L, right, and of course it's periodic after that, right. But nevertheless, I can get any value, right, of reactance, right. If I were to call this J times X and this is minus J times X, I can get any X value, right, by just varying the value beta L between 0 and pi by 2, right. So the range of 0 to pi by 2 is sufficient to realize any inductor or capacitor value, right. So this corresponds to a length that is between 0 and lambda by 4. Okay. So what this means to say is, if I have a transmission line, so this is my short circuit, and its length is between 0 and lambda by 4, this can act like a inductor. Okay. So I can actually incorporate these tiny lengths of transmission lines, right, between 0 and lambda by 4 with a short circuit at the end of it, wherever I need to have an inductor of certain value. Okay. This will of course again be very frequency sensitive. I can only guarantee you that the value of this inductance will be what you want at a very specific frequency, right? Because remember, this is fundamentally dependent on the constructive and destructive interference behaviors, right, which is a frequency dependent phenomena, right? And similarly here, if I have an open circuit transmission line of length between 0 and lambda by 4, this can actually mimic a capacitor. Okay, so I would highly encourage you to go back to the See Think Wonder example that I had given you of a Doppler radar, and you remember those various bits and bobs and shapes that we looked at those circuits, and if you can identify that there are bits that you can associate with these sort of transmission lines, right? So now you can you have the knowledge to say that any portion or any segment of metal can act like a transmission line, right? And these can, if placed at appropriate locations, can actually radically change the behavior of the circuit, right? So you might actually see floating structures that are sort of branching off from the main transmission line that's carrying the signal, which may indicate to you that you have some sort of a capacitor or an inductor that they are trying to emulate, right? And you might have also seen the widths of the transmission lines changing in that example. That may have been an example of a quarter wave transformer possibly, right? So I'd like you to take these ideas of impedance transformation to even real world circuits when you see them next time, right? And the last application is called stub matching. Okay, so remember, in the quarter wave transformer case, we had to introduce a new transmission line of a different characteristic impedance, right? So usually this is not very trivial, right? It's an exercise that requires you to be able to design transmission lines of any characteristic impedance you want, right? Which may involve some iterations. You may not get it right the first time, you may have to iterate and get it correct. But nevertheless, the idea of stub matching is to be able to match the load's impedance to the characteristic impedance, even for complex loads, but without having to introduce transmission lines of a different characteristic impedance, right? So I'm going to tell you that you only have transmission lines of one particular characteristic impedance, but you can attach bits and bobs in any way you like or any form. But I would like you to somehow match the load to the characteristic impedance of the transmission line. So stub matching is the solution for that. Of course, there are single stub matches and double stub matches, and there's a lot of theory that you can work on it. But in this course, at least, I think I'd like to stop with just a very cursory introduction to stub matching, which essentially looks like this. So I have a transmission line of characteristic impedance Z0, and what I do is I introduce in parallel. So this of course can be a short or an open circuit. I'm just giving you a short circuit as an example, right? And this is also of characteristic impedance Z0 and a very specific length L that I need to calculate. Okay, remember that this can give me any amount of imaginary impedance, right? It can be positive, negative, I can do all, right? So if I wanted negative, I would use an open circuit. If I wanted positive, I use a short circuit, right? And on this side, what I do is I extend this same transmission line of Z0, and then I have my complex load ZL that I need to match to Z0, right? So the question is, what are my lengths L1 and L2? Okay. So we'll not go into the details of how to calculate L1 and L2, but I'll just say that there is a concept that you should be readily be able to say that this idea works, right? I'm going to look at ZL by Z0, and I'm going to call that as R plus JX, right? I'm just normalizing it with the characteristic impedance. So this is essentially ZL prime, right? So if I have some R plus JX, I can transform that to any other complex impedance, not any complex impedance, but some relation rule dictated by the impedance transformation equation. So remember that transformation is all I can do, right? In fact, now that you are aware of Smith charts, essentially moving by varying L2, I'll only be along a circle, right? So this is my Smith chart, and this ZL corresponds to some load here. Going along the transmission line gives me access to all impedances that are on a circle that is centered at 0, right, and passes through the load that you have, right. So in the gamma plane, I can place the value corresponding to the load in the gamma plane. Once I do that, all the impedances corresponding to the points on this circle that passes through the load that you have, and the circle center is at the origin, those are the loads that you can access, right. But nevertheless, you can show that at this point, let's call this junction A, where we split off in two directions, one to the short circuit and the other to the load of interest. I can transform this ZL, right, transforms remember admittance is inverse of impedance, right. So I can okay, so I can transform this impedance ZL to something that is 1 plus some imaginary component, right. So I am hoping that you are sort of following the thought, and the idea would be to get this short circuit to transform itself to minus jy, right. So the short transforms to an admittance. It's convenient to work in admittance because these transmission lines are in parallel, right, and when admittances are in parallel, I can simply add them, right. So the idea is that this stub length of L1 terminating in a short circuit essentially maps to an admittance of exactly the negative quantity in the imaginary value that is required to cancel off the imaginary component that you get from transforming the load impedance to the point A, right, to the bifurcation point A. This can always be done, okay. So you can show that for some values of L1 and L2, I can transform any impedance ZL, right, to match to the characteristic impedance Z0, right. So here the only advantage over the quarter wave transformer is I only am dealing with transmission lines of the same characteristic impedance. I am just tailoring the lengths of these, right. All right. So I leave our discussions on transmission lines at this point, okay, and I feel that we have given sufficient emphasis on understanding high frequency, both analog and digital circuits, in the perspective of the idea that fields cannot propagate at any speed they want. They are limited to the speed of light in the medium, right? And this speed of light delay brings about a certain richness in terms of circuit design that we need to pay attention to in order to be able to make high efficiency and well operating high frequency circuits. Thank you.